This is Mathman Eddie back with another topic from a Standard Statistics 1 course. In this video we are looking at something that's called independent events, and this is a topic in basic probability. So what we want to do here is to determine if two events are independent or not independent. So let's take a look at a problem. What we have is an experiment. It says to roll a fair six-sided die. Now when we do this, we know the sample space is 1, 2, 3, 4, 5, 6. These are the 6 possible outcomes, and that's called the sample space. N is the number of possible outcomes, and of course for this problem that is 6. Now let's have some events. So event A means we roll a 1 or a 2. Event B, we roll a 1, 3, or 5. And event C says we roll a 1, 3, 5, or 6. So let's compute some probabilities. We can see that probability of rolling an A is 2 out of 6. There's 2 outcomes in event A. There's 6 outcomes altogether. So we have 2 out of 6, or 1/3. Now, we want to compute another probability, which is not quite the same as probability of A, but we want to compute the probability of A given B. And this is a conditional probability. Now, we could use the conditional probability rule or formula, which says compute the probability of A and B, which is a joint probability, and divide by the probability of B. So let's do that. Now the event A and B, if we look up here at our events, and I'm going to write this down, the event A and B consists of all the outcomes that are in A and they're also in B. And we notice that there is just one outcome. So this is the joint, or this is the intersection of events A and B. Now the probability for that intersection is 1, since there's only one outcome in that intersection, out of 6. And the probability of B is 3 out of 6. So if we do our arithmetic, we have 1 out of 6 times 6 over 3, and we notice that the probability of A given B, which is a conditional probability, is 1/3. Now that we've computed the probability of A and the probability of A given B, let's see what we have. Well, of course we notice that the probability of A is the same as probability of A given B. So what does that mean? That means if we know that event B has occurred, the probability of A did not change. The probability of A is still 1/3. So when this happens, when the probability of A is the same as the probability of A given event B, when these two probabilities are the same, we have a little definition and we say that A and B are independent events. They do not depend on each other. Now, let's take a look at another example. And we have the same experiment, sample space, number of possible outcomes, and the same 3 events, A, B, and C. This time, let's compute probability of A again, which is still 1 out of 3. Now, I want to compute the probability of A given C. And the formula would be probability of A and C, joint probability, divided by the probability of C. Now, A intersection C from the previous example, we know is, actually not from the previous example, from this new example, is everything, all the outcomes that are in A and C. And again, though, it is still just the outcome 1. So the probability of A and C would be 1 out of 6. The probability of C is 4 out of 6. C has 4 outcomes out of a total of 6. And now we can see that the probability of A and C is equal to 1/4. But the probability of A was 1/3. So this example is different from our first example. And what we notice is the probability of A is not the same as probability of A given C. Now, what does that mean? Well, if we know that event C has occurred, then the probability of A did change in this example. So, when the probability of A is not the same as probability of A given C, then we have another definition that says A and B are not independent events. In other words, the probability of A changed when we knew that event B had occurred. So A and B are not independent events. Now I want to take a look at one more example, and this time we're given a table of data, and we can see from here that across the top is the number of pets, and down this side is the age groups. Now we're going to ask a question here about two events, if they're independent or not independent. And the two events are as follows. The age group 0 to 20, we're going to call young. And the column here that says number of pets is 2, that event is going to be T for 2. So, we're going to let Y be the event young. We're going to let T be the event the owner has 2 pets. Now, here's the question. Are the two events Y and T independent? Or are they not independent? So what we'll do is, like the other examples, we need to compute the probability of young and compare it with the probability of young given 2. If these two probabilities are the same, then young and 2 are independent events. And if this probability is not the same as this probability, then the two events are not independent. So let's do some computing. Now, probability of young, we'll go up to our table, and in order to answer this, we need to put some totals on our table. So if we go across our first row, we notice that there are 12, 15, 19 young people, and there are 2, 6, 14 others, and so that's a total of 33 people. And these are actually the totals here for the rows. We need the same thing for the columns. So the number of people that have no pets is 14. The number of people that have 1 pet is 7. And the number of people that have 2 pets is 12. And we notice also that the column totals equals 33. Now, we need to compute the probability of Y given T. So let's take a look at that. Now, by our definition of conditional probability, we would have to compute the probability of young and 2 pets and divide by 2 pets. And we could do that like we did on the previous example. But there's an easier way to get this probability by just using the information in the table. So the information in the table says, hey, let's find the probability of young if we know that the person has 2 pets. So to do this, we go up to the table and say, these are the people that have 2 pets. There's 12 of them. So instead of looking at all 33 people, we're looking at only 12. So we need to compute the probability that the person is young if we know 2 pets, and that's going to look like this. Wow. probability of young given 2, we're going to look at our table. We already said we're only looking at the people that have 2 pets, 12 of them, so that's our denominator. Now, how many of them are young? So we look up here, 4 of them are young. That's 4 out of 12. 4 is our numerator, and we see that probability of young given 2 pets is 1/3, or 0.333. And the big deal here is we've computed this conditional probability, not by the formula, but by going to the table, restricting our sample space down to just those who have 2 pets, which is these 12, and noticing that 4 out of 12 are young people who have 2 pets. And so that's 0.333. So what do we conclude? Well, the probability of young and the probability of young given 2 is not the same. Therefore, we say that the events young and 2 pets are not independent, or young and two pets are not independent events. And we're signing off with this video. Look forward to another video on specific topics in Statistics 1.